Good afternoon. So, my name is Rayleigh-Bénard Instability, and I will be presenting the study that we did on Rayleigh-Bénard Instability in heterogeneous porous media. So, this kind of instability, the Rayleigh-Bénard instability, is responsible of what we call convective mixing. And this phenomenon is present in a large assortment of natural and industrial phenomena, as for example in gravity currents, CO2 sequestration, but also in geothermal energy and seawater intrusion, to mention but a few. So we decided to study the case of the Horton-Rogers-Lapwood problem, whose boundary conditions are presented here. So we impose a number of things. We impose a concentration equal to 1 at the top, a concentration equal to 0 at the bottom, and no flow boundary condition at all the boundaries. And this creates a density stratification, because convective mixing is mainly present in density stratified flows. And this stratification creates what we call the Rayleigh-Bénard instability that is responsible for the apparition of these fingering patterns, these beautiful fingering patterns, that enhance the convective mixing inside the system. So we have developed our own code in OpenFirm. It's a dimensionless one. We use these equations, the continuity equation, Darcy's law, and the advection diffusion equation, and we characterize the mixing using the scalar dissipation rate, which is the rate at which the scalar fluctuations or the concentration gradients are destroyed. We have also extracted the expression of the temporal evolution of the concentration variance, and we can easily find that in steady state this term goes to 0, these two terms cancel out, and we end up having the scalar dissipation rate equivalent to the flux computed from the top. So how do we take into account the effect of the heterogeneity? So we basically use log-normally distributed permeability fields, and then we conduct a parametric study in which we change the variance of the permeability field, the correlation length. At first, we respected this condition, then we found that the heterogeneous porous media that we obtained were weakly heterogeneous, so we had to go beyond this limit. So here we have an example of a normally distributed permeability field with a very small correlation length of 0.02, as you will see it later. And we repeated each case for different Rayleigh numbers, and then we repeat each simulation 5 times. And this gives a huge computational burden. We had around 460 simulations at the end, so it took a lot of time. So here, just to mention that later I will be talking about the mean flux, the flux taken, what we call the convective dominated regime. So this regime is called the convective dominated regime, it's a steady regime. Then we will compare the fluxes of the different realizations between the different correlation lengths at this regime.
Excuse me, is it just time versus the
No, it's the flux, sorry, flux versus time.
Okay.
I thought the quality would be better, but it isn't. So in order to validate our code, we first started by studying what the idealistic homogeneous case. So the variance is equal to 0, no correlation length is imposed. And so when we look, we consider also 6 different Rayleigh numbers. So when we look at the concentration field, we observe that when we move from small Rayleigh numbers to an increasing number of Rayleigh flows, we move from convective rolls to an increasing number of fingering patterns. We also observe that the interfacial area between the 2 fluids is increased because we are boosting the diffusive mass transfer between the 2 fluids. This can also be checked by having a look at the velocity field. Indeed, the velocity field is what characterizes the convective mixing. So here you see that the interface is stretched and compressed at very localized positions. These positions are called stagnation points. They are the cradle of the convection. That's where the convection takes place first. And then, as you move further, you see that we are sharpening these velocity gradients. We can also check it with the autocorrelation function, which gives us an information about how similar the concentration is to itself. And here we see that the number of strips increases when you move to higher levels. Now let's move to the most important part, which are heterogeneous cases. We will first start with the qualitative description, then we will move to the quantitative description. So in the qualitative description, we consider 4 different correlation lengths. 0.02, 0.2, 0.7, 2 different anisotropy ratios. All our heterogeneous permeability fields are anisotropic. So in this case, for a weakly heterogeneous porous medium, there is not much of a difference with the homogeneous one. So we had to increase the correlation length 10 times to see its effect on the fingering patterns. Here, starting from this correlation length, we start to see that the fingering patterns become to look dispersive. And this dispersion is due to the lateral spreading of the fingers. The fingers tend also to coalesce. They tend to merge because they tend to follow the preferential path flows, which are determined by high permeability regions. We can also look at it differently by looking at the effect of the variance. So for a given Rayleigh number of 1000, we have different correlation lengths. We considered 4 different variances, 0.25, 1, 2, and 3. And the same is observed as you move to higher variances, as you move to highly or strongly heterogeneous porous media. The fingers start to look dispersive, and they start to coalesce, which what we call the late mixing regime happens earlier in that case. Let's now move to the quantitative description. So there are 2 ways to describe convective mixing in that case, whether through the mixing, which can be characterized by the fluxes, or the mixing state, which can be characterized by the probability density function and the intensity of segregation. The concentration variance, which is basically the width of the probability density function, also gives us some information about the mixing state. But since it's already included in the intensity of segregation, so we will only talk about the intensity of segregation. So if this I is equal to 1, the system is completely segregated, and if it is equal to 0, it's completely uniform. And as you know, mixing is the process that transforms a disordered film into a uniformly distributed one. So we want to know how does the heterogeneity affect the mixing state. So first of all, I thought the quality would be better. I'm sorry for the quality if you cannot see it. So when we look at the fluxes, so for different variances, for the smallest one, no, we cannot really distinguish between the different correlation lengths. But as we move to higher variances, we start to see that the case with the highest correlation length of 0.7 takes higher fluxes. And when we compare it with the case with the anisotropy ratio of 7, the green one, we see that the case with the smallest anisotropy ratio takes higher fluxes, which means that the smaller the anisotropy ratio, the higher the fluxes. If we look at the fluxes, these are the fluxes as a function of the variance instead of a function of the Rayleigh number, then we can see that for the smaller or weakly heterogeneous porous media, the increase in the fluxes it's very slight. Then when you move to the highest correlation length, we start to see that it's steeper compared to the other cases. Now, I'm not going to go into all these curves in details, don't worry. So we are just going to look at the strongly heterogeneous case. So for this case, for the case of the correlation length of 0.7, these are different variances. So first of all, let's look at the effect of the Rayleigh number. So here we have 6 different Rayleigh numbers. What we observe first is that increasing the Rayleigh number, which basically is reducing the diffusion, narrows the PDF. But it narrows the PDF, which means that the system gets less segregated. Then, when we move to higher variances, the width of the PDF becomes higher, which means that the system becomes more segregated. So that as a conclusion, we can say that the higher the variance of the permeability field, the more segregated the system. The higher the variance also. Well, the same is observed in the case of the intensity of segregation. The blue curve corresponds to the homogeneous case. So when we compare the intensity of segregation with the homogeneous case, even for the smallest correlation length of 0.02, we see that the intensity of segregation is higher compared to the homogeneous case, which means that the system is more segregated in the case of heterogeneous porous media compared to their homogeneous counterparts. Here, we cannot see, I suppose, but here it's just to say that when we increase the correlation length, the system becomes also more segregated. So another way of describing convective mixing in heterogeneous porous media is by looking at the interface width. So here what we have observed is that increasing the correlation line and the variance makes the interface more stretched and compressed. So when you have a lot of low and high permeability regions, your interface tends to be stretched and compressed at these regions. After finishing all these simulations, we decided to make an upscaling of the heterogeneous simulations, which basically consists in looking for equivalent homogeneous porous media of all the heterogeneous porous media that we did. So it was quite a tedious operation because I had to do it for more than 400 simulations. And so here, since we have a 2D domain, we need to look for the effective permeability in the x-axis and in the z-axis. And we extracted this simple expression because the Rayleigh number, the classical one, does not include any heterogeneity in its expression. So we expressed this new Rayleigh number, longitudinal Rayleigh number, by solving, simply by solving the Darcy's law, imposing a gradient in the longitudinal direction. We can find the k-effective x, and we can thus define a new Rayleigh number. The same has been done in the transverse direction. And we also defined a new Rayleigh number, which is expressed as a function of the dispersion coefficient. So we know from Gelar and Axenus that the dispersion is proportional to this term, and we end up finding this. We are still working on this part because we need to express these new Rayleigh numbers as a function of the anisotropy ratio, the effective permeability in the x-axis and in the z-axis, in order to have a more general. As a conclusion, so we can say that increasing the correlation length of the permeability makes the fingering patterns look dispersive. The number of fingering patterns tends to decrease as we increase the correlation length. Well, this is a consequence of the preferential path flows created by high permeability regions. The intensity of segregation increases as we increase the Rayleigh number, but it takes higher values when the system becomes strongly heterogeneous. The smaller the anisotropy ratio, the higher the fluxes. The interface is more stretched in the case of heterogeneous porous media, and we finally conducted an upscaling of this Rayleigh number based on these different effective permeabilities and dispersion coefficient. And with that, I thank you for your attention. If you have any questions.
Yeah, I do understand it. All the results that you showed to us, it's just for a specific distribution of log k. I mean,
so we have different realizations. It's a statistical study. So you have, for each permeability field, you change the variance and the correlation length. Length along the x-axis.
Yeah, but for each this correlation length and variance, how many fields?
5. Each
5.
Yes.
So the result that you show us, it's like the mean of these 5.
Absolutely, yes. It's not very significant that we couldn't afford to. In some papers, we can find that some papers say 10.
Yeah, no, way more.
But the code in OpenFOAM was really slow. It took a lot of time to converge, so we restrained the number to 5.
Okay, but is it sensitive?
Absolutely. There is a lot of numerical dispersion, especially when you increase the Rayleigh. You didn't finish your question, sorry.
No. Yeah.
It's very sensitive.
Because, I mean, everybody says you have to do hundreds if you want to.
Yeah,
Exactly.
To get something which is, let's say, a proper Monte Carlo series.
Yes, but I have been already running this for 2 years now. We are just writing. We have just started writing the paper. Sorry. So.
I feel very sorry that I missed it. I came in at the end, but
You can see the recording.
yes, thank you. But based on your abstract, it looks like you were looking at Gaussian fields. Have you
Multi-Gaussian.
thought about doing this for even more strongly heterogeneous, like binary ternary.
Yes, according to geologists, it's better to take truncated, log-normally distributed
Yes.
fields. But for now, we just looked at the case of the classical case of log-normally distributed fields. Someone else will do it.
You should do it.
Yeah, I don't think I have time for that. I only have 2 years left. So.
Oh, careers are long.
Okay.
After the PhD.
Yes. Any other questions?
So when you did the upscaling, it seemed to me that you're amplifying the Rayleigh number for the hydraulic peak.
Effective permeability, yes.
But this is an effective permeability with dimensions, I understand.
No, everything is dimensionless here.
Is dimensional.
Everything is dimensionless.
So it's a Rayleigh number that takes somehow into account this effective permeability. But okay. I was wondering because then I thought this Rayleigh number now is with dimensions. So you say it's dimensional.
So the Rayleigh number is it's a buoyancy forces over diffusion forces. So they all consider all dimensions cancel. But what's the point of having dimensions or not?
No, when I saw that equation, I was wondering why and you now using dimensions. But now you were looking about dimensions.
Because the Rayleigh number is always by definition.
Yes, it's like the Pickley number.
Yeah, of course.
Yes.
Thank you. One last question.
Yes.
So when you show these patterns of convection in the heterogeneous mediums,
This something what?
when you show the patterns of convection
Yes,
in
the
the
fingering
in
patterns.
the heterogeneous medium, so these patterns are somehow representative of the steady state of the system, or are they steady, these patterns?
They are all in the steady state, yes, what we call the convective dominated regime.
And well, can you explain again, please, the meaning of a picket PDF? Well, yeah, in this, yeah, the next figure.
Yes? The peak. Yes.
I mean the, yeah.
So here, when you increase the Rayleigh number, your PDF gets narrower. And when the PDF gets narrower, basically the variance, the concentration variance gets lower, and thus the system gets less segregated because you have only two strips, let's say 2 or 3 strips of concentrations which have the same value. Instead of having a lot of gradients, you are destroying the gradients by increasing the Rayleigh number. We're sharpening them at the same time, but destroying them at the same time.
Can you please describe what you were saying about the transverse dispersivity? You said it's not relevant in 2 dimensions, but I did not fully catch
Well,
that.
according to the paper of Rayleigh-Bénard Instability, which is a very old one, when you have a 2D domain, you can neglect the transverse dispersivity. You can only consider the longitudinal. To be honest, I don't know how to.
You mean for the convection process?
Yes. You see, the fingers seem to move laterally when they coalesce, because at some point they start merging, they start following the preferential paths of high permeability regions, and then they tend to spread laterally. That's why maybe we tend to neglect the transverse permeability. Maybe I'm mistaken, huh? Thank you for your questions. Thank you.